Hello and welcome to this short podcast about counting and addressing. This podcast is a little math review that we need to do before we begin on the second half of the semester. Hopefully the content in the slides are going to be obvious to some of you, maybe many of you. That's a great thing, but experience shows that when I teach this course, often some students have problem with some fundamental discrete math skills. And we need to be solid on those skills so that we can handle what's coming for the remainder of the semester. And so although this is not actually OS material, we're going to need it to teach OS material. So I'm doing this now, and if you find going through the lecture notes, which hopefully you've done before you're watching this, or maybe you're watching this at the same time, that's okay too, and you find that you're going to have difficulties with this, then you have plenty of time to practice before we actually need this in class. We should start needing this in maybe a week, maybe 10 days. All right, so first, units of storage. The smallest unit of information need the bit, and if you don't know why it's called a bit is a contraction of binary digit. Okay, and the basic unit of memory, the byte, that's 8 bits. Hopefully we all know this. And then we count kilobytes, megabytes, gigabytes, terabytes, petabyte, exabyte. And every time we multiply by 2 to the power of 10. So 1 kilobyte is 2 to the 10 bytes, and 2 to the 10 is 1024. Okay, and then a megabyte is 2 to the 10 kilobyte, which is 2 to the 20 bytes, which is about 1 million, right? And so on. So the I above means that we're doing powers of 2, right? Often people forget the I, which leads to confusion. But the thing to remember, for instance, here, the example in red, 1 gigabyte GB is actually 10 to the 9 bytes, like a gigameter. But 1 GIB is actually 2 to the 30 bytes, which is close to 10 to the 9, but not exactly the same, right? And typically we pronounce them the same, we say gigabyte, right? But then when you write, if there's an I, you know it's powers of 2. For the rest of the semester, we're gonna almost always do powers of 2. And so hopefully I won't forget any I in my units. Important, you know the order above, right? Kilobyte, megabyte, gigabyte, terabyte, petabyte, exabyte, right? So if at some point I ask you on an exam or a quiz or in class, how many gigabytes in a petabyte, it should be easy for you to tell me 2 to the 20, okay? We're going to use exponents and logarithms at a very, very basic level. So basically, we're going to multiply number that are exponents, take the inverse, and divide, right? So here we have the standard formulas for dealing with exponents. But in fact, our exponents are always going to be powers of 2. And so the 3 basic formulas are when you multiply 2 to the x times 2 to the y, the result is 2 to the x plus y. When you divide, it's 2 to the x minus y. And a special case is when you divide 1 by 2 to the x, then you get 2 to the minus x. Okay, so hopefully all of this is completely obvious because of you've taken calculus in the past, right? Similarly, we use logs. Log base alpha of alpha to the n is equal to n. That's the definition. But again, we're going to use alpha equal 2, meaning we only do base 2. All right, so log base 2 of 2 to the n is equal to n, which is different from the natural logarithm, which is not base 2. Right? In computer science, because of binary, we typically consider log base 2, and typically we don't write the 2, we just write log. Right? And typically it doesn't matter because we do asymptotic computational complexities, as you've seen in 311. And then, of course, a big O of log 2 of n is the same thing as a big O of log 10 of n because they differ by just a constant factor. All right, so the formulas in red are all the math we need here. And so again, I'm going to assume this is a no-brainer and that everyone is solid with this because you've taken calculus. If somehow you're not, which I can't fathom how that could be, well, you have some time to refresh your memory, I guess. Now, when studying operating systems, especially when we deal with memory, what we're going to do now, we need to count chunks or groups of bytes in some memory space. So if I say how many 1 megabyte chunks are there in an 8 megabyte file, well, that's easy, it's 8, right? But then if I say how many 4 kilobyte chunks are there in an 8 gigabyte file, maybe that's not easy. Maybe some of you can do it in their head right now, but I kind of doubt it, right? But the way to do this is very easy. It's to use powers of 2. And typically we want results expressed as powers of 2 anyway, because the numbers are going to be too large to write them out in decimal, right? So we're always going to write powers of 2. And so since everything is a power of 2, those kind of questions that, like example 2 above, are very straightforward. So before getting to powers of 2 though, let's review the basic principles. If I say how many groups of 12 parking spots are there in a 252 spot parking lot, right? I'm using parking lots as an example. There could be many other examples, crates of oranges, just to make it clear that this has really nothing to do with the computer memory. It's just about counting things. And the answer to that is 252 divided by 12, which happens to be 21. I picked the numbers that were they divide in this case. And so if I say how many groups of X thingies are there in a set of Y thingies, well, then you guessed it, the answer is Y divided by X. Okay, so that's just a generalization of the above example. And so when I say how many 2 kilobyte chunks are there in a 1 gigabyte, let's say maybe a 1 gigabyte file, well, the answer is 1 gigabyte divided by 2 kilobytes. And now we express those in powers of 2s, going back to bytes, and we find the answer. So 1 gigabyte is 2 to the 30 bytes. You have to know this right off the bat. 2 kilobytes, well, it's 2 times the number of bytes in a kilobyte, and a kilobyte is 2 to the 10 bytes. Therefore, 2 kilobytes is 2 to the 11 bytes. Therefore, the answer to the question is 2 to the 30 divided by the 2 to the 11, y divided by x. And because we know how to do divisions of exponents, that's 2 to the 19. So the answer to the question, how many 2 kilobyte chunks are there in 1 gigabyte, is 2 to the 19. And if you really want to know the answer as a base 10 decimal, well, then you have to compute 2 to the 19, which is a huge number. Another one, how many 8 kilobyte chunks are there in 128 megabyte? Same thing. 128 megabyte is 2 to the 7. 2 to the 7 is 128. It's a good idea to know a few powers of 2. I, for instance, always kind of know that 2 to the 6 is 64. I don't know why. Years after years, I've memorized that one. So if 64 is 2 to the 6, well, then 128 is obviously 2 to the 7. Right? It's okay to count on your fingers initially, but it'd be nice to have a few signposts. Like, I don't know, 2 to the 6, 64, 2 to the 10, 10, 20, 24. And then, like that, you can multiply or divide by 2 and quickly find the answer. So 128 megabytes is 2 to the 7, 128, times the number of bytes in a megabyte, which is 2 to the 20. So 128 megabytes is 2 to the 27 bytes. Similarly, 8 kilobytes is 2 to the 3, which is 8, times 2 to the 10, 1024. And so 8 kilobytes is 2 to the 13 bytes. Therefore, the answer to the question is 2 to the 27 divided by 2 to the 13, which is 2 to the 14. 14 being 27 minus 13. Okay, so that was about partitioning things into chunks, and we do that very often. We partition a pie into slices, a computer's memory into bytes, a file into blocks, an address space into pages. We're going to spend a lot of time doing that one, a disk into sectors, and so on, right? And so once we've partitioned our thingies into blocks of thingies, then I should say our set of thingies into blocks of thingies, then we need to address the chunks. We need to name them, right? Addressing means really naming. And naming using, well, a name often in the human world, but in the computer, we name them using a number. We will say you are chunk 0, you're chunk 1, you're chunk 2, and typically we name them like that in sequence. And so, of course, we've already seen what addresses are, right? Each byte in RAM is addressed by a number, and we call that the address. And an address is stored in binary format in the computer, like all numbers. And then we use the addresses. For instance, we have instructions in the instruction set architecture, something we talked about probably the first week of the semester, where we have an instruction that says store the value 00110011 at address 11010001, right? So the address and the data look the same, they're just numbers. So the key question is, what is the range of addresses that we need to address all chunks we have for some problem we have to solve? And every chunk needs to have a unique address. We want the smallest possible range of addresses to not waste address bits, right? If I have two things to address, let's say I've got two houses, I'm going to call the first one 0 and the second one 1. Meaning I've got 1-bit addresses. It is wasteful to call the first one 00000 and the second one 00001. right? Because then the leading zeros are the same for both houses. They're wasted, and yet I would have to store them in my computer memory, for instance. So for instance, turns out I have a house example here as well. Okay, we have 7 mansions in Honolulu, like as we do, and we want to address them via binary addresses. So I could use 3 address bits, and I call the first one 000, the second one 001, and so on, and the last one is 110. With 3 bits, I can address 2 to the 3, meaning 8 houses. And so in this case, we're wasting 1 slot, right? With 3 address bits, 3-bit addresses, I can address 8 houses, and I got 7, right? But then with 2 bits, I can only address 2 to the 4 houses, 0001, 1011. And so that's not enough, because I need to have 7. So what we do in this case, we say for addressing my 7 mansions, I'm using 3-bit addresses, right? We don't want to use 4 bits, because that's too many, it's wasteful. With 4-bit addresses, we can address 16 things. But in this case, we only have 7, which is less than 8, which is half of 16. Therefore, we can get by with only 3-bit addresses. Okay. So hopefully this makes sense. And so the one thing that I keep repeating over and over during the next couple of weeks of the semester when I teach this course is always the same. If you have 2 to the n thingies, then you need n-bit addresses to address the thingies. If you have fewer bits, you can't address them all. If you have more bits, then you're wasting address bits. Okay. More generally, if you have n thingies, then you need ceiling of log 2 n bit addresses, right? Because maybe n is not a power of 2. So here we have to take the ceiling, which is take the largest number, right? In our previous example, we had 7 houses. Log base 2 of 7, if you take your calculator or computer, you'll find is 2.8, right? And so therefore we have to use 3 bits to make sure we can cover everything. If we took the floor, we would use 2 bits, and then we can address only 4 houses, not 7. So the actual mathematical formula is ceiling of log 2 of n. But when n is a power of 2, well, by definition, this is n, which is what the red sentence here says at the top. Often we address things that are powers of 2, so we're not going to see that ceiling a lot in what we're going to see next, and then therefore we won't write the log 2 either, because the log 2 of a power of 2 is trivial. And so that's great. And why do we have a lot of powers of 2? Well, because of binary and because we build the system. So I'm not going to tell you, oh, I built a machine and it has 37 bytes of something, right? Because 37 is a prime number, not even worse than not a power of 2. And so we're going to design systems that are convenient to work with, and therefore powers of 2 are going to show up everywhere. Now, a little bit more discrete math. Say you have a parking lot that consists of a long row of n parking spots, and they're numbered 0 to n minus 1. We always start numbering things at 0. That's what we do in C, C++, Java, and in computer science in general. We structure the long row into blocks of small n parking spots. You know, in real life that happens. Maybe you want to assign those blocks to different companies, whatever. And we're going to assume for simplicity that small n divides big N. Otherwise, we have a weird block at the end that is not full. Let's forget that for now. And so here is some very simple discrete math. The x spot in the parking lot, so x is therefore a number between 0 and n minus 1, is the x mod b spot in the floor of x divided by b block. We're going to see an example where this makes sense. Here's another statement. The yth spot in the zth block is the z times b plus yth spot in the parking lot. Okay. So we're going to see an example. You can then pause and rewind and look at those formulas again, or maybe you have the lecture notes on the side. So say I have a parking lot with 3,000 spots, and we structure them in blocks of 100 spots. What is the index of spot 3,212 in its block? Well, the index is 3,212 mod 100, which happens to be 12. You can see that's pretty obvious. The first spot in the first block is spot 0. the first block in the second spot is spot 100. So therefore, spot 3200 in the first spot of a block. And therefore, the one that is that plus 12 is therefore the 12th spot in the block. Another question. In what block is spot 3212? Well, that's easy. The answer to that is the integer division of 3012 by 100. Or, as I wrote before on the previous slide, the floor of the non-integer division. And so in this case, what we get is, what is 3212 divided by 100? 32, again as an integer division. So spot 3212 is in block 32, which is the 33rd block, because the first block is block 0. And then if I tell you, oh, I want to park my car in spot 5 of block 20, and then you ask me, okay, well, what spot is that in the whole parking lot? I need to give you the global index, meaning a number between 0 and, in this case, 2,999. And so the answer to that is, I'm in block 20, every block is 100. And so the first spot in my block is going to be the spot of index 20 times 100, which is 2,000. And then I am spot 5 in there. Therefore, overall, that spot is spot 2005. So that's all. Now, some of this seems probably very disconnected from the material in the course, but that's going to stop appearing that way very soon. In the upcoming lecture, we're just going to do a few simple in-class exercises, and of course, I'll answer whatever questions, and we'll go a little bit further, right? You must be absolutely comfortable with all this, and as computer scientists, counting and addressing should be, part of your DNA, right? So if what I just went through seems completely outlandish, well, you have time to try to go back, come to office hours, and go back to your basic math textbooks and try to catch up. If it doesn't seem outlandish, but seems like you can't go as fast as what I did right now, well, that's just practice, right? You have to know how to do these things reasonably fast. And that's it. And again, when you go out for job interviews, you cannot afford to not be comfortable with counting, addressing, and powers of 2, right? So it's also what this is about, because you'd be surprised how often those tiny little stupid questions pop up in random job interviews. Okay, thanks for listening. See you in class next time.